to be on reducing water consumption in ethanol manufacture. The Energy Independence and Security Act, also called the Clean Energy Act in 2007, mandated that renewable fuels will be about 36 billion gallons by 2022, I believe. And that of that, ethanol is going to be a big portion of that, even mostly cellulosic type ethanol production. So once that act was passed, and even before that, because of fairly generous government subsidies, ethanol was considered to be the next gold rush. So a lot of people were investing in ethanol plants, and so because of the profitability in doing so. Now, but ethanol is not just, you cannot just manufacture ethanol without other inputs. And one of the more critical inputs in the process is water. And so when people started putting ethanol plants in places that did not have enough water resources, they were depleting groundwater sources fairly rapidly. So this quickly became a national topic of debate. Are ethanol plants too thirsty? Are they depleting groundwater resources? And so very quickly it turned from ethanol being a good guy in the energy portfolio to ethanol being both something that is taking away food from the masses because of the corn that is being used to produce ethanol, as well as whether they are being responsible because they were depleting groundwater resources. So going very quickly, the debate turned to whether ethanol was environmentally friendly. And one of the main reasons for that is the consumption of water within these plants. And so you can literally talk about throwing cold water on the idea of ethanol being environmentally friendly fuel source. So you can see that a lot of headlines, and in fact, very close to home, when the Anderson people were interested in setting up a plant here, some of the questions raised was, how much water is it going to consume? Will it actually make a difference to the Mohammed Aquifer? And actually in places like North Dakota and Minnesota, there have been instances where ethanol plants that have been cited have drawn down the groundwater resources sufficiently to be alarming to their local residents. So So these have consequences, these headlines, and they also force choices. So for example, the Cardinal plant in Minnesota was denied a permit because the local rural water system could not provide them the water that they needed. And similarly, another Cardinal plant in Nebraska was granted a permit only after they could purchase offsets elsewhere. So when you are trying to put a site in ethanol plant in one location, people are making these choices. Is it really important to our local development? Where can I offset the water that's being used, and so on and so forth. So today's topic, we're going to focus on, and so this is a study from Minnesota where you look at, this is the amount of water that is used, gallons of water per gallon of ethanol produced, and the data is for Minnesota plants. And they have tracked how much water is being used in ethanol production. So you can see that from 1998, the water use intensity, which is the amount of water that is used to produce a gallon of ethanol, has steadily dropped. And today, more recent plants are in this band of 3 to 4 gallons of water per gallon of ethanol produced. But at the same time, the number of plants, even though the water intensity has decreased, the number of plants that produce ethanol has increased. Therefore, the cumulative amount of water that is used in ethanol production has also gone up. So the question then is, what can we do about it? The question that I will try to answer today is, can water used in ethanol plants be reduced from this 3 to 4 gallons of water per gallon of ethanol? If so, by how much more can we reduce it? How can we reduce it? And is net zero water consumption achievable? This has been talked about. And what it really means is, can you produce a gallon of ethanol with no water input in the net sense, right? So is that possible, achievable? And what would it cost? And so I'm going to address the cost question first, and then we will talk about the rest later. So the take-home message is that water is not a major cost component in ethanol production. So there are other inputs, for example, corn, electricity, natural gas, yeast, enzymes. These are all much higher cost items in the variable cost of production of ethanol. So if you are paying 43 cents per kilogallon of water, 1,000 gallons of water, and let's say that was the baseline, then if you calculate the variable cost, let's say that is the 100% is the baseline. If the cost of water doubles, this hardly budges compared to the baseline. If it doubles again, yes, it does go up a little bit, but not a whole lot. So water can go up by 1,600%, but in terms of variable cost of production, of ethanol production, it will only go up by 3% or a little bit more than 3%. So water is not a major cost component in ethanol production, which means that you can afford to pay more per 1,000 gallons of water without really affecting your bottom line. So that is the take-home message that I want you to kind of consider. Because so then we will start addressing this question: is can water used in ethanol plants be reduced? And so before doing that, I just wanted to step you through the process of ethanol production, point out where water is used within ethanol production, and then we'll talk about how we can reduce the quantity of water that is used. So basically, you start with corn. This corn is then broken into small pieces in hammer mills. You use water here to basically make a slurry. And this would be considered what is called a processed water. Then you cook it, you break it down, then you add enzymes to break down the starch, then you use the yeast to do the fermentation. The fermentation reaction produces heat by itself. So when yeast takes up sugar and converts it into ethanol, along with the reaction, some heat is released, and that heat has to be removed from the process, and so the fermentation tanks have to be cooled. So there is a cooling requirement that has to be done here. The fermented broth then has to be, you have to evaporate the ethanol from the fermentation broth, and for that you have to use steam, which is basically water that is converted into vapor state, and then you have to condense the ethanol that is in the vapor state to liquid, and you need to use water for the condensation as well. So water is used both as steam as well as for condensation and distillation part, and then the part of the grits from the fermentation that are left behind has a lot of water, and so the excess water is evaporated in an evaporator. Again, the evaporated water is then condensed. Again, you use cooling water for that purpose. And you also use cooling water for cooling the final product as well. So water is used in many different ways in many different parts of the plant is really the key message here. So if you look at water and how it is normally obtained in an ethanol plant, typically water comes from a well in most places. If not, in some cases, they might purchase it from a city water utility, or in other places, they might get it from a surface water source. This water by itself is not in a state that can be used directly within the plant. It has to be purified. So it goes through some kind of a treatment process. Depending upon the quality of the water, the treatment process can be very elaborate or it can be fairly minimal. But in all instances, you do produce a treatment waste that comes from this process. So there is water that is coming out as effluent during this treatment process. Then the treated water is then used within the process for slurrying corn, growing yeast, as steam for cooking and evaporation and so on, and for cooling. And I talked about some of those places where you would have to cool different parts of the process as well. So we basically are working with one plant in Rochelle, Illinois, and we have monitored the water consumption over a period of 1 year, and we have kind of broken it down to different categories of use. So what this graphs shows is that average water consumption that they're using right now is 545 gallons per minute to produce 100 million gallons of ethanol per year. Of this 545 GPM of water that is brought into the plant, about 248 gallons per minute is used for cooling purposes. 223 gallons per minute is sent to the water treatment facility, which is basically comprises of multimedia filtration and reverse osmosis. And part of the water is used for slurrying corn, and that is about 75 GPM. So then if you were to break down the consumption in terms of, you can see the total amount of water used is about 3 gallons of water per gallon of ethanol, of which about 1.88 or 62% of it is used for cooling purposes. And the processed water is about 0.41 gallons per gallon of ethanol, and the boiler water, which is for steam production, is about 0.37. You can see that that in the process of making pure water or water of sufficient quality, you produce quite a bit of waste here, which comes from the reverse osmosis and the multimedia filtration processes. And that accounts for a significant portion of this 3 gallons of water per gallon of ethanol. So that's about 0.41 gallons, or about 13% is coming just from the waste from the treatment process itself. So the first opportunity then for you to reduce water consumption is to minimize the amount of water treatment waste that you produce. So then if you take a look at that in slightly more detail, you will see the water treatment process brings in about 222 gallons per minute, of which, and then produces reverse osmosis water of about 151 GPM and produces a waste water stream of about 71 GPM. Of this waste of 71 GPM, one of them is the filter backwash, which is 11 GPM, and then there is something called the reverse osmosis reject water, which is another 60 GPM, accounts for the total amount of waste produced in the water treatment. So then we looked at whether this wastewater was really waste, or was it of sufficient quality to be actually used back in the process. So what happens in a multimedia filtration? So this is a multimedia filtration system. Basically what you're doing is you are pumping your water through this to remove what is called ion particles really in it. So most of the water is really very good quality, but may have very, very small quantities of ion contamination that is being removed here. This ion then forms a top layer on this bed that is used for filtering the water, and every so often, typically about every half an hour or so, there is a backwashing of this filter to remove this layer of iron oxide material that is deposited. And that is the waste material. That's what contains, that becomes the waste stream. And this flushing process goes on for about 18 minutes or so. But most of the contaminant is actually removed within the first 3 minutes of the backwash. And then if you start looking at the rest of the water that is produced for the rest of the cycle, and it's still being backwashed, and it is being sent to the wastewater treatment holding pond, this water is actually of really good quality. It's equivalent to the same quality as city water, and therefore there is really no reason why this water should actually be sent to wastewater treatment. Rather, it can be reused back in the process. So that is your first opportunity to cut back on waste. And if you did that, you would save about 4 million gallons per year. And this is a fairly simple fix. All you have to do is adjust your wash cycle so that you actually get rid of the most important part of this, the contaminant buildup in this tank, and so that you end up not having to require the rest of this water that is currently being wasted. So this is one opportunity to reduce waste. It will reduce about 4 million gallons per year in this facility. The second opportunity is to increase the reverse osmosis recovery. And what I mean by that is you're taking in about 211 GPM of water within the reverse osmosis plant. And the reason you want to do reverse osmosis is so you want to remove dissolved ions within the water. And you want to produce water that has very low total dissolved solids content, and that is considered the filtered water. So during this process, because you are splitting the water in the reverse osmosis into a low dissolved ion, low TDS value water and a high TDS value water, and what happens is you have to reject or you have to waste a certain amount of water that is called RO reject, because this water has higher TDS, and it also has ions such as calcium, which can form scales. So just like in your bathrooms, if you have hard water, you will find a thin film of white stuff that forms in your bathtubs because of the hardness. Similarly, these membranes can be coated by these high hardness water, and therefore you would want to make sure these membranes are only operated to a certain extent with a certain amount of calcium, and to avoid precipitation of these hardness ions onto the membrane, you would be rejecting a certain amount of, or you would be allowing a certain amount of the water to go waste. So given, and this is a function, how much water can you actually, if you have really, really clean water coming in, and you just wanted to do some polishing type operation, you can get almost all of this water out here. If this water is really, really hard, then you may only be able to get 50% of the water, purified water, out of the system, and the other 50% might be waste. For the water quality present at this particular site, we can easily attain 75% recovery of water for this particular water source. So if I had 100 gallons of water coming in, I should be able to get at least 75 gallons of water coming out as pure water, and I should be wasting only about 25 gallons per minute. But the way that the system is operated, they are only operating at 71% recovery, as opposed to the design level of 75% recovery, and therefore it just requires a change in the operational practice for them to be able to bump up this recovery rate from 71% to 75%. If you did that, and there is really no reason why they can't do that, it is only a question of operational control and monitoring of the system, then you can save about 5 million gallons per year. The second thing is, we went ahead and looked at this water quality, and we have to go through a number of calculations to see what is the achievable recovery rate without causing problems in the system. And if you were to go through the process of calculations and stuff, it turns out we can actually get 85% of this water out without causing fouling of these membranes. And if you were to actually bump it up to 85%, then we can save about 17.6 million gallons per year. And again, this is purely using the equipment that they have right now, but monitoring and operational procedures have to be changed so that you waste less water and so that you can recover more here. So that's the other opportunity that you can do. The third opportunity is to minimize cooling tower waste. And what a cooling tower does in an ethanol plant is basically, I told you that there are a number of processes within the plant where water is used for condensation of, say, alcohol vapor, for product cooling. So this is what is called excess process heat within the plant. This process heat has to be removed from the plant, and the way you do it is by circulating cold water through those pieces of equipment. So they take away the water from the plant, and in the process, this water gets heated up. So this hot water then goes into what is called a cooling tower, and it is contacted, and you blow air through it, and in the process of blowing air through it, you evaporate a little bit of the water from this stream coming in, and that is this billowing vapor that you can see. And in the process of evaporation, the water gets cooled down, and then this water is recirculated back into the process. But this cooling tower also is susceptible to scaling by salts or by bacteria and stuff like that. So to make sure this cooling tower operates efficiently, we will have to waste a certain amount of water that's called a blow down. And that, in this particular instance, was about 85 gallons per minute. So the question is, can we reduce this amount of blowdown that is being currently wasted? And the answer turns out to be yes. So I won't bore you with the details of what it means, but essentially you can operate the cooling tower more efficiently, and if you did that, you would save another 11 million gallons per year. Yes?
Can you say what percentage of the water is lost for the evaporation that you're sending through?
Quite a bit. So in fact, if you went back to the first slide, the cooling tower is really where the bulk of the water is lost. About 62% of the water is lost in the cooling tower as evaporation. Right. This 85 gallon per minute is a much smaller portion of that.
I realize that, but the total water sent through the tower
is about,
what percentage?
Oh, it doesn't matter because it's a recirculation. So for example, so let's go back to the previous slide. Oops, what did I do? All right. Okay, so do you see this? This is called makeup water, right? This is the amount of water that is coming into the cooling tower. And I told you 545 gallon per minute is what we're taking in as a total. And then 336 GPM of that is going into the cooling tower. Most of this 336, about 248 gallon per minute, is actually evaporated, and this is the rest of it. Okay?
More than 50%.
Oh yeah, it's usually the evaporation about 85% of the total makeup. 85%. Typically, that's what you would use for design purposes. Yes. So if you were to operate your cooling tower more efficiently, then you can save another 11 million gallons per year. So we have talked about several opportunities. So let's kind of take pause and kind of see where we are with all of these different opportunities that we have identified, and how much have we really accomplished. So if you reuse filter backwash, we can save about 4 million gallons per year. If you run your reverse osmosis system more efficiently, you can save another 5 million gallons per year if you just go up to 75% recovery. Or you can save 17 million gallons per year if you operate at 85% recovery. If you minimize the blowdown, if you go to what is called a cycle of concentration of 5, you can save 11 million gallons per year. If you operate it even more efficiently, which is possible at this plant, you can save about 18 million gallons per year, right? So you add it all up. You know this is your current 300 odd million gallons per year is your current consumption of water. So you end up saving between 6.5% of water compared to today's baseline to about 12% savings by just through these waste water minimization opportunities. Not a whole lot, but better than where we started out with. So to go further, we must reduce in other ways. We have to find other avenues to reduce water consumption. So one question is, can we reduce the processed water that is used, which is about 0.41 gallons of water per gallon of ethanol, which would amount to about 40 million gallons per year. Now it sounds more interesting. Now we're talking some bigger numbers here. So if to do that, we have to find a way to substitute for the processed water that's being used with city water right now. So then we go around the plant looking for alternative sources of water that you may be able to use in the process itself. And so if you make a list of what's available within the plant, so these are the streams. The filter backwash is available. It's a small quantity, about 11 GPM. Its quality is pretty good, 500 milligrams per liter total dissolved solids. It's available within the plant. RO reject, its quality is variable depending upon how we operate it. Right now, they are operating at this level. We think we can easily operate at this level, and we can even go up to this level. But then the salinity of the water then is increasing, and the question is, can we use it in the process? So that is the thing that we have to think about. The cooling tower blowdown, right now we have about 62 to 85 GPM depending upon how we operate. And if we operate it really efficiently, our TDS will go up to about 1765 milligram per liter. If you operate less efficiently, you'll get about 1396. There is also evaporator condensate that is already being used within the plant, and I will talk about this later. It is already being used. It's not available right now, but there are certain ways in which you can creatively combine some of these streams so that you can actually cut down the water, and I'll explain that in just a moment. So just to give you an example of how you might substitute for the processed water using an alternative water source, we will take the cooling tower blowdown, which is about 85 GPM, and we will match it with the process need, which is about 75 GPM. So what I'm going to do is I'm going to ask the question, since I have cooling tower blowdown, which is roughly the same quantity that is required in process, can I take the cooling tower blowdown water and actually use it in process for process purposes? So that's the question, right? And so I have somebody here who actually helped me answer the question, Dr. Singh from the Agricultural Engineering Department. He is an expert in fermentation. And so what he did was he took the water, we did all the analysis, and so we know exactly what the levels of different types of contaminants are in this water. And Vijay basically took this water and he did a series of fermentation trials with these. So then his control was DI water, which is really, really pure water. So he would then take sugar, yeast, or basically starch, yeast, add his enzymes, do his magic, and he'll look at how the glucose content was going down, which means the yeast is actually utilizing the glucose. He also looked at how much ethanol was being produced. And then his comparison was this cooling tower blowdown water, right? And so he did this a number of times. And essentially the point being that there's no difference in the yeast's ability to ferment cornstarch to ethanol when it was using cooling tower blowdown water, which had much higher levels of dissolved solids or ions in comparison to DI water. So the question is, so the answer is, you can actually use fairly low quality water for performing these kind of fermentations. You do not necessarily have to have the highest water quality that they're currently using. So that really is the main thing. So that means we can we have essentially then established that we can take a waste from a different part of the process and use it to substitute water needs in other part of the process. So that's really what we've done. We've taken, it's called cascading. So you want to take something that is wasted in one part of the process and match it to another part of the process so that you can minimize the total quantity of water in the whole system. So that's what we're trying to do. And this then, if you can take this water and use it in your fermentation process, will save you about 40 million gallons per year. So now we're talking some more interesting, exciting numbers. But that is not all. There is really no reason for us to stop there. If a little bit of wastewater from a different part of the process is good, why not a whole lot more? So let's see how much we can push this envelope and how much water we can reduce. So here you have a different way of rearranging the process blocks within the plant, and for combining other wastewater streams, such as the backwash, the RO reject. I'll take my cooling tower water, and then I actually put it through a reverse osmosis system, and this is purely for schematic purposes. So what I do is I basically purify this cooling tower, put it through an blowdown, put it through an RO, and I get an RO reject from that, which is fairly high now in TDS. If I combine a portion of that reject water with the RO reject and backwash, which have much lower levels of TDS, then I can produce a combined stream that is still pretty good for process purposes. So now what I've done is I've combined 3 different process streams and use wastewater streams, and I'm substituting it for the processed water. If I were to rearrange it this way, then I can save about 71 million gallons per year to compare to our baseline of 306 million gallons per year. And this is not the only arrangement possible. There are multiple ways in which you can do it, and there are multiple technologies you could use. Now, the question that would be asked typically if I were making this thing in an industrial facility, how much is it going to cost? So I want you to think back to the first slide I put up. It doesn't matter how much it costs. Even if it costs twice or thrice what you're paying right now, you still shouldn't have to worry about it making an impact on your bottom line, because water as a cost component is really, really a small portion of your total that's really not what you need to focus on. You need to focus on things like yeast and enzymes and stuff like that, which are much more expensive, not necessarily worry about it. So there is plenty of opportunity to actually reduce water consumption within these plants. So remember I mentioned briefly that there is something called the evaporator condensate that is already being reused within the plant. It turns out that how much dissolved solids I can tolerate in my process. So I can't actually take seawater and put it in and expect the yeast to actually ferment and produce ethanol efficiently. That's what won't happen. So the question is, how crappy can the water really get before I start seeing some problems, is really the question we are trying to ask. And the answer is, it all depends upon if there are other types of stress factors that are being added to the water from other parts of the process. So things like lactic acid or acetic acids, these kind of organic acids which are present at very low concentrations in the evaporator condensate, which comes from a different part of the process, has a huge influence on what the yeast's ability to tolerate higher levels of total dissolved solids. So here the real opportunity is, if you can clean up this particular stream, which has these acids, and if you could lower it down using some other technology, then you can actually probably use water maybe of 5,000 ppm or 6,000 ppm solids content, total dissolved solids content, whereas right now most people tend to limit it to about 1,000 ppm maximum in their plant operations. So those are the ways in which the different parts of the process kind of link together to determine what is the minimum amount of water that you need in a process. So in fact, that will be one of the few things that we will be exploring in the future, is how can we take this evaporator condensate stream and look at ways to reduce we'll be actually analyzing it for these acid content levels and see how we can remove it. And then based on that, we can then see how much more crappy this water can be without affecting the process. So that's really what we want to do. So getting back to the first question, can water be reduced from its current level? I assume you would agree that yes, you can do that. If so, by how much? 10% is very easily done, not a problem, not very expensive, not expensive. You can reduce it by as much as 25%. There are a couple of things I'll come back to about the regulatory hurdles. So essentially what we have done then is taken this water treatment waste and put it back and substituted it for the processed water. That's how we have achieved this 25% reduction in this whole thing. And we can reduce, depending upon how we do this, to about 2.3 gallons of water per gallon of ethanol by doing a combination of these things that I just talked about. One of the things there are some regulatory hurdles. It's not that you can just start doing this, because the cooling tower, what you're doing is you're adding some polymers, which are meant for scale control and corrosion control and stuff like that. And that water, if it's going to go into the process, it's going to end up in what is called the dry distillers grain solubles. The market for that is in animal feed. So the question then becomes, are you adding things to the animal feed that should be there or not? So the question is, that will not, you cannot just add things to an animal feed without going through the proper regulatory procedures. One way then, so you have to actually get permission to do that. So that's the first hurdle. The second thing is, you have to make sure that whatever is being added to the animal feed is what is considered as generally recognized as safe, or GRAS status. And so what that means is you have to then start using GRAS status polymers for cooling tower control, so that you will be allowed to put it back into this processed water. And it turns out those polymers are available. They're a little bit more expensive than the normal polymers, which are not GRAS status, but it can be done. So that is the regulatory hurdle that you have to overcome. This is a kind of an interesting question. Is it too radical for a lot of people? And the plant that we worked in, they said, well, we are willing to consider it, but they're not really moved on it. So while at least in theory they're willing to consider making these kind of changes, in practice we have to wait and see if they will actually do it, whether they will feel comfortable enough to do it, and whether it will really happen. There is actually, I'm told, a plant in Arizona which is actually doing this cooling tower blowdown recycling back into the plant. So maybe it's a question of creating awareness so that if they know somebody else is doing within the industry, they might also start adopting those kind of practices. So getting back to your question about the cooling, that is the elephant in the room. That's really where you're using the bulk of the water, right? So unless we get a handle on this, we're not really going to make, we cannot, what is it, net zero is an impossibility. So one way to cheat, and I like to cheat a little bit, is instead of using fresh water, if we had access to another source of water, which is treated municipal effluent, maybe I can take that water and use it in my cooling tower, all right? So that's the question. So what if I did that? If I did that, then my fresh water reduction is basically I'm using fresh water only for my process and my boilers, and I'm using treated municipal effluent for the cooling tower purposes. If I could do that, my fresh water consumption is 1.3 gallons of water per gallon of ethanol. So you can reduce fresh water by from 3.06 to about 1.3 gallons. And there is a plant in Corning, Iowa that is actually doing this, and there are a couple other plants also that are doing this. But philosophically, the question that you struggle with is this really legitimate reduction in water, or is it merely shifting water from one source to another? So how many of you would agree using effluent would be a legitimate reduction in water as opposed to, so 1, 2, 3, okay, 4, 5, well, a lot of people. I somehow have a difficulty with that. I'm not sure if that's really legitimate reduction of water, because that water can be used for other purposes too. There's always an opportunity cost and that kind of thing. So, but it's not a bad way to do it, and it's in many ways it's the only practical way for some plants which do not have access. So we can use this treated wastewater. So we have a year's worth of analysis of the water quality, so we know exactly what to do. And we can take this water and reuse it in the cooling tower. The problem with this, there's another regulatory hurdle here, is that this particular ethanol facility is permitted through its NPDES permit. It can only discharge water from this cooling tower to about 1,000 ppm TDS, or total dissolved solids. It goes to a holding point within the site. It turns out this water that is coming from the effluent treatment plant is about 1,200 or 1,300 ppm to begin with. So it's not like you can just cycle it through the tower and put it into the holding plant. You actually have to build a pipeline first from this plant to this plant, and then back from this tower back to this plant for you to be in compliance with existing regulations at this facility. So if you can renegotiate your NPDES permits, this is certainly a doable thing. If not, you have to figure out, you have to send it back to the utility. But this is certainly it costs about $2 to $2.50 per 1,000 gallon to actually take this water from here to here and back. And so compared to the current cost of about $1 a 1,000 gallons, which is what they're paying for. A second opportunity is, why use water at all? In these cooling towers, why do you have to use water? Can we not use a different medium? So air can be used as a cooling medium, and then there will be no blowdown. So this will go away. But given the climatic conditions of Illinois, there will be certain periods in the year where air alone cannot accomplish the cooling. So you will have to have some kind of a small cooling tower of a lower capacity than what we need right now. And that will require, so there will be a need for a small tower. It also increases power consumption by 2.5 to 3 times compared to the current power consumption for operating these cooling towers. And power turns out to be a much more important cost component in ethanol production, the variable cost, than water. So therefore, anything that increases power consumption will be viewed a lot less favorably because it has a direct impact on the bottom line, as opposed to, say, the cost of water, which I told you is not very sensitive to the cost of water. So the third pathway then that you might have to reduce water consumption is to reduce the cooling load. So if you have to remove less heat from the process, then you have to evaporate less water to accomplish that cooling. So this is the third way that you can accomplish. And you can do that. If you have thermotolerant yeasts, or if your plant is integrated so that processes that require to be heated and processes that require to be cooled are matched, and this is called process integration, and if you can tightly match those together, then you can reduce the amount of water that is being used. How much can you reduce it? By process integration. Today's ethanol plants use roughly about 36,000 BTUs per gallon of ethanol right now in terms of energy for carrying out the process. If you did complete integration within the plant of where you're matching the heating and the cooling loads, you can reduce it by about 17% to about 31,000 gallons per minute, 31,000 BTU per gallon of ethanol, I'm sorry. And then there are other ways in which you can reduce it by a factor of 50% after that, but that requires that your distillation columns and your beer columns all have to be broken up into little chunks, 2 or 3 columns instead of 1 column, which means so that total energy requirements are reduced. But that option is a lot more expensive, and most people would not do it unless there was a really good reason to do that. So through process integration, you can reduce it maybe by about 17%, which is certainly doable. But again, it is for a plant that is already built, the retrofit costs are usually very high, and it may not make much sense to do that. For a new plant, it may make a lot of sense. And finally, so we talked about water treatment waste and then putting it back into the process water. We talked about the need for process integration, which will reduce the need for steam. But then you can also do one other thing, which is you can recover process water. And I'll just give you a brief example of how that might be done. This is a superheated steam dryer. So before I do that, so the corn that comes into the plant has about 0.37 gallons of water per gallon of ethanol. You inject steam for cooking and stuff like that, and then there is processed water that is used for slurrying. So this, after it goes through, most of this water then is evaporated out in the dryer, and you can get about 1.1 gallon of water in the dryer exhaust per gallon of ethanol. The conventional way of doing this is basically you take your DDGs, which is your wet product, and you're evaporating about 25 pounds of water per bushel for a 100 million gallon plant. So you're basically taking hot air, you're blowing it, drying it, and that hot air plus moisture is being vented out into the atmosphere, and that is the moisture that is lost. In the superheated steam dryer scheme, this water is then captured and it can be reused within the process. So that gives you another opportunity to actually recover water from a source, and that is quite a bit of water that you can recover and reuse within the process. I think, Vijay, you told me there's a plant in China, is that right? That's doing this? And there is a plant in North Dakota that tried it, but seems to have given up. I just talked to them this morning for some other reason. So the question is net zero water consumption possible? Given what we know right now, we can, I think, go to about less than 1 gallon of water per gallon of ethanol is within reach. Net zero, maybe it's an aspirational goal, maybe not necessarily that realistic, but it's worthwhile kind of keeping that in the back of our mind and kind of working towards attaining that. So with that, I think I will stop. If there are any questions. Well, as a final thought, so you want to reduce freshwater use. You can do it in a number of different ways. We talked about cooling load reduction a little bit, alternative cooling technologies. You can use alternative sources of water, or you can conserve water. So if you put them all together, you can certainly get below this 1 gallon of water per gallon of ethanol. No single one will help you achieve that. So if there are any questions, I'll be happy to take them. Yes.
Okay, I got two actually.
Right.
Is all cooling non-contact?
The cooling. What do you mean non-contact? Yes.
Doesn't come in contact with the product at all. At plants like this that are located near major bodies of water, is consideration given to single-pass non-contact?
I think the EPA has come out with the new source guideline, which does not allow you to do that. And this plant is not near a source of water. It is not. Okay. So, yes.
do some of these.
All right. So my first slide was basically to address that point because each of these different opportunities have different costs associated with them, and we can talk forever about how much, whether it's $2 a 1,000 gallon, $3.50 a 1,000 gallon, $7 a 1,000 gallon. It doesn't matter because you can actually spend quite a bit of amount on water itself without affecting your overall economics of the plant, which is really the bottom line I'm concerned with.
Right. So then,
Right.
to me, the only incentive for anybody doing anything is to get the Illinois Commerce Commission to put a special surcharge on any water used by an ethanol plant, and that's the leverage, because otherwise I don't see any leverage.
Or if you could do that, that's certainly one way to do it. But you also have to be mindful that if you did that, more plants will shift to Iowa or to Wisconsin. Right.
Because that's the only way you'll get it to really save
Sure.
water.
That's one way to do it. Sure. Yeah.
Do you have any estimates for sand lossing plants?
No, I do not. Right. The numbers I've seen, and you may be aware of the same numbers that I'm seeing, is 6 to 10 gallons of water per gallon of ethanol. Much more than this, so that's going to be a problem because they have to actually use water in the front part of the process and then use the same amount of water on the back side of the process as well. Yes?
If I wanted to get energy out of corn without using any water, I would burn it.
Okay.
And that would give me 7,000 BTUs a pound,
Mm-hmm.
as opposed to about 1,375 BTUs for the ethanol you'd get out of that pound of corn. So that's 5 times more energy, not even considering all the energy that goes into this.
Right.
So for transportation fuel, once we figure out how to store energy, electricity, this doesn't make any sense at all, does it?
See, I think MTBE was the reason that it was being phased out in ethanol was being used as an oxygenate. The way this started off was for as oxygenate. So ethanol was being used as a substitute for MTBE. That was the start of where it was being used for transportation fuel, right? And then it became more and more you wanted to use it for fuel value. Yeah, but yeah, there are many different ways in which you could do it. If you could, there are advances in so many different fields where you can produce electricity at a fairly cheap cost. And if you can store it, if you can solve all those problems, sure. But in the short term, you need a transitional strategy. And so I think this fits some of that.
Push it a little bit more, that if I only took 70% of the energy and left 30% as biochar, now I have carbon negative energy, and I can improve my soil equation.
Sure. Mm-hmm.
All of the examples that you spoke about rely on evaporative cooling, except for the
That's
dry cooling
Mhm.
option that you mentioned at the end. Why wouldn't you consider the use of a heat pump?
For example, you could use geothermal type. You can think of geothermal systems where you could take this hot water and pump it through the ground, that kind of thing.
A heat pump just like a refrigerator.
Yeah. So
You would use the cold end of the heat pump to condense
Right.
water and the hot end to heat it.
Typically the way these plants are designed is for a 10-degree Fahrenheit difference. So the water that is coming out of the cooling tower is about 85 degrees Fahrenheit. When they put it through this plant, it'll come out about 94, 95 degrees Fahrenheit. So the difference to do that, it just turns out to be pretty expensive to do that. Now that it cannot be done, when I talk about this expensive stuff, the cost of the heat pump itself, even in other places like distillation columns where the temperature difference is much higher and where there is more energy that you can extract usefully, even there heat pumps may or may not make sense depending upon the configuration which you put.
Basically, all this evaporative cooling
Mm-hmm.
technologies are doing is taking water out of the oxygen
Absolutely, and I agree with you.
and evaporating
Mm-hmm.
it, and then putting all of the salts back into the surface water. And you call them regulatory hurdles. I call it protection of water quality. So why can't we divert attention to technologies that squeeze the solids out so you have a solid waste?
So there's a plant in Galva.
You can do that.
There's a plant in Galva, Illinois, which makes ethanol, where they actually take all the water, evaporate it, crystallize the salt, take all the water and put it back into the plant. Now, what is the cost for that? That's about $7 a 1,000 gallons. And they can afford to do that, or they want to do that. So there are, all these things are individual plants make their own decisions. And so, yeah.
What is the conductivity of the RO water?
I know the TDS is less than 10 milligram per liter. And so I don't know exactly the conductivity. I don't know. Yeah, right. Yeah.
In what process is the RO water?
So the RO water, most of it is used for steam, for boiler, as a feed to the boiler water. And then some of it is actually used to blend with the city water coming into the cooling towers to lower the TDS of the cooling tower so you can get higher cycles of concentration. So that's really. Yes. No, softeners are actually used as a polisher after the RO in this particular plant because the boiler requirement, it turns out that that the water quality for the boilers, you have to have a demon system before that. So, yeah.
What is the Eli and Alpha temperature in cooling tower?
It changes, but it's about 95, 96 degrees Fahrenheit. Outlet is about 84, 85. Again, that will change with season. Yes.
One more question, going back to the question from the lady in front about cost. If it's $7 a 1,000 gallons to totally eliminate the total dissolved solids from the effluent, that comes out to about 2 cents a gallon of ethanol.
Now you're talking about that being of the same order of magnitude as some of the other cost components, like yeast. And so it actually moves up the chain of variable costs, and so it will actually make an impact at the bottom line at that point.
But I mean, that's nothing compared to the level at which the public now subsidizes ethanol production.
Yeah, I mean, these are, I think, policy debates which I don't necessarily. This is purely more of a technical, thing, and yeah. All right. Thank you.